বিশ্বজিৎ, আমায় শোনা যাচ্ছে?
হ্যাঁ, পার্থ শোনা যাচ্ছে?
শোনা যাচ্ছে, শোনা যাচ্ছে।
শোনা যাচ্ছে, শোনা যাচ্ছে।
আচ্ছা,
না, একদম চুপচাপ ছিল তো সব।
হুম হুম।
Good evening. Good evening to all of you.
গুড ইভিনিং।
গুড ইভিনিং।
So on behalf of the Department of Mathematics and on behalf of the organizing committee, I, Dr. Arnab Gupta, as a joint secretary in the international webinar on algebra and topology. Today, I welcome you all for the second day. So today we have two technical session. One now in session one, the speaker is Professor Parthopratim Ghosh from University of South Africa, and I am feeling lucky personally. I can tell that I have enriched with his teaching in the St. Xavier's College, Kolkata during the year 1997-98, and he will be talking about on the notion of universality. So, and the second speaker is Professor Mohammad Akbari Tutka Boni. He is from the Department of Pure Mathematics, Faculty of Mathematical Sciences, University of Gulian, Iran. So, may I request Dr. Bishwajit Mitra to act as a chairperson in this session and conduct this session. Thank you, Dr. Mitra.
Thank you, Arnab. Okay, let's start the first technical session of the second day of this webinar. I like to convey my sincere thanks to the organizing secretary, Professor Prashanto Sinha, for inviting me to chair this technical session. I am truly honored to introduce our speaker, Professor Parthopratim Ghosh. I was fortunate that I was postdoctoral fellow under his excellent guidance when he was a lecturer at the University of KwaZulu-Natal, Durban. However, he is at present associated with the Department of Mathematical Science, University of South Africa, Florida, South Africa, as a senior lecturer. He is a figure of vast experience both in teaching and research. He completed his master's in statistics from Indian Statistical Institute, Kolkata, one of the leading statistical institutes around the world. After completion of his master's, he began his professional career as a statistician at Bharat Margarine Limited, Park Street, Kolkata. But after 1 year, he left the job and joined as research fellow at the Department of Pure Mathematics, the University of Calcutta, under the joint supervision of my own supervisor, Professor S.K. Acharya, and Professor K.C. Chattopadhyay of Bardhaman University. His PhD title was Rings of Ordered Field Valued Continuous Functions. He started his teaching career as a lecturer in mathematics at St. Xavier's College, Kolkata. During this period, he used to coordinate and teach in the development of the course at the Reverend Gore Center of Higher Mathematics, aiming to train the students for higher education in mathematics. Eventually, he changed his research area to category theory and later joined as postdoctoral fellow at the Topology and Category Theory research groups at the University of Cape Town, South Africa, under Professor Hans-Peter Kunji. Later, he left the job of St. Xavier's College and joined the University of KwaZulu-Natal, Durban, South Africa as a lecturer in mathematics. He was also involved for training students for South African Mathematical Olympiad. He is also one of the founder member of the Indian Linux Users Group, which is quite interesting. He authored several qualitative and informative publications in various reputed journals around the globe and delivered conference talks as well as expository talks in different national and international platforms. Now I request Professor Ghosh to deliver his expository talks on the notion of universality. So Professor Ghosh, you may continue now.
Thank you for a very kind introduction. I'm really thankful that you have asked me to speak in this seminar. I thank the organizers and the coordinating person for this. This is the first time that I am giving a webinar, so there can be a little bit of glitches. I usually like to have a lecture in a place where I can see the faces and interact with the students. So if you have questions even in between, you could use your chat box to send the question if I may see it, or else alert the coordinator or the chairperson with it. I hope you can see the digital board, which I have already started sharing.
Yes, we can see your digital board, also your voice clearly.
Thanks. Well, I work in categories, and categories are full of arrows. But this arrow, the first initial arrow that I drew, is not a categorical arrow, although it is. But let me say, this roughly represents the development of mathematics some 200 years before, when, not 200, a little more earlier, when it was almost like a single line. Every mathematician kind of understood every other mathematician and could be interested in others' problems and share these problems with each other. Cantor gave us the nice paradise of sets. It is one of the nicest paradise that one can have been given. But after this came in several other developments, and the development started to get bifurcated and then further bifurcated. Until now, it is almost a big mist. An idea of it would be obtained if you look into the MathSciNet page, MathSciNet classification 2020. It has almost 100 broad classifications, and each one again has 10. So it often is now a picture like this, that someone on a branch like this doesn't even care or think about a branch over here. The goal and the dream of a category theorist is to put a single line again. That means to capture almost all of this development in a single sway. Now, what is the mystery behind this category theory? It is not new. People have been working, I would say, with categorical tools from even the first day when they started to do mathematics. And the idea was, in fact, in this little word called universality. Or what I would try to replace this word by trying to find the best possible option, the best choice. Now, in the first part of my lecture, I will try to give several examples from different areas of mathematics to convince you of this best, how to make this best choice, how we have been doing this best choice, and how it actually pervades almost every place in mathematics. So let me start with the first basic example of the greatest integer. Greatest integer less than or equal to a real number. So what is it? Firstly, it is an integer. Secondly, it is less than or equal to x. And the last one tells us one of its best properties to say that it is the greatest. So if I have an integer and it is less than or equal to x, then it is this. In other words, what am I doing? I have my set of integers and my set of reals. I have included my integers in the reals. And I take an arbitrary real from here and try to find the best possible thing over here, which is smaller than that chosen real. Okay? Let's, well, this will be very, very disconnected, obviously, because I'm trying to bring out a common phenomenon. So we will be looking into several examples. So here's the second one. The second one actually spans over many places. So let's look into the first case. Suppose you have a function. From a set x to a set y. You look into the power set of x. Immediately we know that there is two other functions. One is given by the inverse image, and the other is the image. I'll very strangely write it like this. And there is a reason why I'll do it. Now, how are these two functions related? Well, suppose I take something from here and something from here. Okay? Then I know that A is a subset of, this is a undergraduate exercise, if and only if its image is a subset of B. So if you start from A, what is its image? Given this B, image is the largest subset such that in the inverse image contains that set A. Okay? So that's exactly the notion of an image. However, there is yet another one, which we usually do not see But here is it, something can be seen very clearly now. I'll write it like this. You know that a function can be very well denoted by its stock diagram. So this is my function f. Suppose these are the points which are leftovers, okay? And then suppose we have, so for each element over here, you have its stock. Over it, right? And so on for each one of these in the range. I mean, now I look into, for a subset A of X, I'm defining so this is a definition by an implication. So it means, so remember this is an implication. So vacuous implication using our usual logic works. So this statement shall be true even if this is the hypothesis is false. That means, so for this set contains all the elements which is not in the range plus what? Plus some more. So which element shall it? That means if you take a set like this, which cuts through all these stocks, then there will be nothing. But it will contain all those y's whose stocks are already inside it. Okay? Plus all those that's the meaning of this statement. Okay? So you get a clear-cut idea of what it is. And interestingly, why I brought this is, interestingly, one can show F inverse B is contained within C if and only if B is a subset of for LFC. Okay? So if I take a subset of X, C, that will contain B if and only if that C contains. So again, the same idea. For all F is the smallest subset with this property. Okay? Now let's try and give a meaning to this. Why did I use these strange looking symbols? They are not at all strange once we consider this special example. Say you take the first projection. Suppose you take a subset of X cross Y. That means a relation. What is this? This is its range, which you usually write as this. What is this? This is X belongs to X such that, let me write it here, such that there exists an X in A such that X is such what did I? There exists a U in A such that X is equal to Uy. Sorry, pi 1 U, which can be expressed in a much better way by saying that this is the collection of all X such that there exists a Y in Y such that XY is a member of A. And similarly, if you look into this, this is the collection of all X in X such that for all X in A, okay, so it contains this whole strip pi 1 inverse X. Oh, sorry. So for all Y, let me write it in this easier form. XY belongs to it. Okay. So as if I have tried to bring up this quantifiers in terms of a function and reframed it, and that explains this usage. But in fact, this goes in much further in the development. We'll come back to it if time permits. But let's see, what are we doing? Over here, there is something special that we are doing in both these examples. Both the power set of X and power set of Y are partially ordered sets. So we now generalize to the case when X and Y are partially ordered sets, and we have two order preserving functions. And the property that we have written over here, or even earlier, this can be now written in terms of this situation as for all X in X and for all Y in Y, if X is less than or equal to Y, if and only if X is less than or equal to GY. Now, in the theory of partially ordered sets or ordered theory, this is very well known a system of functions. It is usually called by the name of Galois connections. So you see, even our image, pre-image, and its generalization, how it comes over here, falls in this way of finding the best possible thing. In the Galois collections, in our practice, what happens is we try to find for each Y the best possible image of X which satisfies this, and that's the whole idea behind it. Let me utilize this Galois connection a little further. You know that if you have an equivalence relation, on a set X, this equivalence relation, giving this equivalence relation is the same as giving a partition, and it gives you a quotient. Which is usually called the factor map. And how are equivalence relations compared? Well, very natural, since these are subsets of X cross X, I'll say an equivalence relation psi is bigger than rho if everything related by rho is also related by psi. Now let's try to give an order. On surjective images of X. So, what are my objects? My objects are surjections. Let me develop this idea of writing a double arrow for a surjection. So, it's a pair. It's a pair. Say, if you want, you can look at it as a pair or as a function f, whatever. So f is a surjection from X to Y. How am I going to, how do you think about ordering them? So if I have another one, when shall I say something like this? Well, this is not new. If you have learned about it is something like the ordering of compactifications, but okay, here is something simpler to reconcile. Well, what is a surjection doing? It is a kind of labeling things. So this should be bigger if the labeling by G is already explained by the labeling F, which means that if there exists an H from Y to Z, such that G is HF. Okay. Now, with this, it turns out that it is easy to show that it is reflexive and it is transitive, but the antisymmetry fails. Antisymmetry fails. On the other hand, what happens is if I have this will happen if and only if there exists a bijection such that G is HF. So if we have if H is a bijection, essentially we can think, so labeling done by Y and labeling done by Z are essentially the same. It's just the bijection is producing the translation from Y to Z. So essentially, although we don't have an order, but if we quite agree that we will not quite distinguish between such labelings where there is a bijection, then we can think pretty well that there is an order, there is a partial order. How does this affect us? Well, if you look into this, let me look into surjections of X as a partially ordered set. Surjections of set as a partially ordered set, and let me look into equivalence relations on X. Obviously, I know that given an equivalence relation, I have a surjection, the factored map. And what do I take on the other side? Suppose I am given a surjection. So this is a surjection. And I take this set. This is the set of all x, x prime, such that fx is equal to fx prime. This is usually called the kernel pair of f. Now, this is obviously an equivalence relation, and the equivalence relation induced by this surjection. So every surjection induces an equivalence relation. And it is now very simple to check. So I just keep this for people whom it is new. Suppose I take a surjection over here as I did, Fy, and I take an equivalence relation rho. Then what do I want to say is something like this. Kf is bigger than or equal to rho if and only if this is an equivalence relation, if Fy is this is rho x pi rho. Now, what is this? If you see, this is essentially what you call in your algebra lectures the first homomorphism theorem. So you are saying that you have an equivalence relation on rho, and you have, so this is your x by rho. So if whatever you have equalized by rho is already equalized by f, then you have a morphism from here to here, right? So see again, so this is again a special case of a Galois connection, which again comes out from this choice of best objects. Let me go to another place. Remember, one of the standard examples in equivalence relations in undergraduate classes was you take the additive monoid of natural numbers, and from there you give an equivalence relation on n cross n, and somehow after a long arduous process come to construct Z. On the other hand also, you do almost the same trick. Why almost? You take the multiplicative group of non-zero integers. By Z star, I mean the non-zero ones. And you make the multiplicative. So you take the multiplicative monoid of non-zero integers and you make this over here. What are you doing exactly? What are you doing? So you start off with a monoid, and somehow you are trying to produce a group. And the procedure is exactly the same. You can, I'm sorry, you start off with a commutative monoid. The commutativity would be required. You start off with a commutative monoid and you make an abelian group out of it. And you run through the same exercise that you do in undergraduate classes. It works. And what does this construction give us? It shows us that suppose if you take this monoid would be embedded inside this group. Let me write this group as, let me write this group instead of a G, let me write this as G of M. It is embedded. So, we are putting a monoid inside a group, a commutative monoid inside an abelian group. So what? I'm saying it is the best. In what sense? Suppose you take any abelian group and suppose you take any monoid homomorphism. By which I mean that f of xy is equal to fx plus fy. Okay? So then when you tell me this, there exists, the construction tells us that there will exist a unique group homomorphism such that it restricts when it is restricted to M, it gives me exactly this. I'm not going to the details, but this is exactly, think what you have done. If you take over here your naturals, and this is your Z, how, so what is this in embed? It is just the embedding. Now, how will you take Z to this? Well, an element of Z is a difference of two naturals, and then you know what to do. If you can represent that in several ways, the construction tells you all of them will give the same answer. Okay? So that's what this construction procedure is. So you are trying to bring in the best group. This is usually called the Grothendieck group of M. Okay? So that's another one. Let's come to rings. Now there are various things over here. It has two operations. So it's a set with two operations and satisfying certain equations and so on. So firstly, it is a set. So the first thing that I can think of is a set over here. Then there is a monoid structure there. The multiplication makes it a monoid. Yes, ring. I mean a ring with an identity. And homomorphisms, therefore, will always preserve the identity. And then I have another structure that's an abelian group. So there are three other notions connected with the ring. Now suppose I give you a set X. Given any set X, can I think of the of a ring which is in the best way, best possible ring? Yes, I can. And that is called the free ring. And what is it? Well, what do I mean by a ring? Well, I'll be taking products and sums. Okay? So, formally speaking, I will be looking like something like x1, x2, possibly another x1, things like this, x1, x3, x2, and so on. So I take some finitely many symbols from X and try and create all possible finite products. These are all formal products though. And I would add them. So things like this, right? That's what this free ring is about. Or in other words, I'm thinking in terms of the ring of polynomials with coefficients from R coming from coefficients in Z the symbols, the variables, the indeterminates are coming from the set X. Okay? And obviously, how is this related? Well, every set is obviously contained in it. And if you take a ring, and if you take a function, you know again the same picture. This can extend uniquely to this, which restricts on X to be this original function, right? So again, this same. So this is the best possible ring that I can make out of any set. Well, the same thing happens for monoids. If I take a monoid M, then what I will do is I will construct what is known as the monoid ring. Okay? And over here, if I take an abelian group A, what I'll do is I'll take the tensor ring. Just for more clarity, what is, okay, let's spend a little more time. What is this tensor ring? What is this tensor ring? Well, this tensor ring is Z plus, you remember, these are direct sums of abelian groups. And so on. And then there is a natural, since I know that if I take a K such product, say K such products, and an M such product, then this is isomorphic with K plus M times such tensor. These isomorphisms will obviously give me a binary operation of addition on this. Okay. Now, And that again satisfies the same property. That means A would be, as you can see, A is already sitting inside TA. And if you take hold of any ring, but this is just, so this one was a function, this one was a ring homomorphism. Well, this is an abelian group homomorphism, and this is again a ring homomorphism. So you see, this construction of tensor algebra is nothing else but finding the best possible alternative. Okay. So similarly over here, this is actually the set of all maps, from M to Z whose support is finite. You add them pointwise and you multiply them exactly as you multiply polynomials. So your multiplication over here would be so that's how you do it. In particular, you see, this gives us another little story. It shows us that the polynomials are also the best possible constructs. If I take it, it turns out that if you do the same construction, you replace Z by a commutative ring, and instead of M, you take your naturals with addition. This is nothing else but your Rx. So what you're saying is that your polynomials are also such certain best. So it is the best ring alternative to this monoid of natural numbers. So that's the best way in which you can embed. If you want to embed your naturals inside a ring, the best one is the polynomials. Okay. So since I came to tensor products, that takes me to the next one. Let's look into it. Remember bilinear maps. Suppose you have abelian groups. This is bilinear if for each fixed A, this function from B to C is a group homomorphism, and for each fixed B, this from A to C is a group homomorphism. So that means, hence the name bilinearity. Okay. Now, is it possible? So the question is, so again the question is, well, obviously, when I say bilinear, it is not, it is, well, fixed in each variable, it's linear. It's a group homomorphism. But it is not a group homomorphism by itself. So is there a best representation of this? Is there a best group? Or is there a way to represent this? So the best representation And that is exactly the tensor. That is exactly the tensor product of. So what is it? So what is the tensor product of two groups? Well, it is a group. Firstly, it's an abelian group such that there is a bilinear, there is a standard bilinear map, which is often called the canonical one. A canonical bilinear map going into this group, such that whenever you have a bilinear map, it factors through. So this is a bilinear map. And this is a group homomorphism. This factors through this tensor product, and this is the tensor product of that. So again, you see, the tensor product is the best way to represent bilinear maps, and that's how it comes up into a picture. Taking this, another side of the story is one side, since multiplication in particular, if you think about multiplications, well, and if you think about the ring axioms, so for instance, what are the ring axioms? One is the abelian group part, and the other side is saying there's a multiplication and there's this distributive law. What is this actually saying? This is saying that if you look into this map, this is actually a bilinear map. This is actually a bilinear map. Now, since we have already learned about tensor products of groups, so this bilinear map, therefore, would correspond to a group homomorphism. So this is a bilinear map. This is the multiplication. This let us write as M. This is a group homomorphism. So because I'm taking R as an abelian group with the addition. So just think. I have done something very, very deep over here. I have replaced somehow this Cartesian product symbol by this strange kind of a product. So in other words, we know with this Cartesian product, we often call this a binary operation. So can I call it a binary tensorial operation? Let's call it. And indeed, it turns out that if I think of this as a tensor operation, as a binary, just like a binary operation, but the multiplication, the Cartesian product replaced by this, then this binary operation turns out to be associative for a ring. Or in other words, it turns out that with this kind of a multiplication, I have a monoid. Of abelian groups. Very strange looking construction, right? But still, I have some kind of a monoid of abelian groups. And strangely, the same construction repeats if I replace abelian group by K modules, where K is a commutative ring with identity. Then we have the tensor with respect to K, and with that same thing, we do have a monoid of K modules, and they are nothing else but K algebras. So this is not just a isolated situation. So rings are exactly monoids of abelian groups. K algebras are nothing else but monoids of K modules. Well, there are several such examples once we start looking beyond. What are topological monoids? They are monoids of topological spaces. And interestingly speaking, well, it comes out at a later stage. One can reframe the Ekman-Hilton principle. By saying that monoids of monoids are nothing else but commutative monoids. Okay, so suddenly you see, thinking in terms of these best things, the best choices, suddenly produces a huge similarity between quite a disparate group of things which used to be studied separately. Let's take up some topological examples. Say, let's start with a topological space. Where am I? So suppose I have a topological space X. So given a topological space, what? Obviously, it is a set plus another thing. It's topology. Now, can I have suppose I start off with a set. Can I immediately make topologies on this? Well, obviously, one best way is to make the discrete topology. And how does the discrete topology look like? Well, it looks like, so you started off with this. Let me call the discrete topology as dx. Well, if you look at it in this way, obviously if you take this set X and you take any topological space, and you take a function, the discrete topology on X is the one which ensures that this function is continuous. Okay? So it is, in a sense, the best. There's also the best over here obviously doesn't mean it is, we are kind of, there's also another way of finding the best. This is indiscrete. And how is it? If I call it I of x, then this is continuous. Then the problem is that suppose if you have, but this time it gets reversed. Suppose if you have a function like this, then this function becomes continuous. Okay? So the underlying set of this is still x, the underlying set of this is, so on the same set x, I can give two topologies. But what are these topologies? What are these topologies? Remember, the topologies, this is a set of subsets closed under arbitrary joints and finite meets. Well, this brings us to, well, obviously this is a subset of the power set. We don't bother about the next thing. This brings us to the next part of the story, is something which is nowadays known as a frame. What is it? It is a complete lattice. In which finite meets distribute over arbitrary joints. So the topology of a set, topology on a set, is actually nothing else but a frame. Okay, and indeed, I can write this in another way. This as a set. Why do I say as a set? In fact, as a frame even, is same as all continuous maps. From X to the Sierpinski space. Okay, so this is same as this, and this observation actually gives rise. So if I start from topological spaces on one hand, and on the other hand I look into frames, then from here I know I can go by taking the opens. And there is also another side of this story. So given any frame L, there is a best. Topological space. Called the set of points of L. And it turns out that again, there is a similar, it is the best in that sense, in the sense that I was trying to say. So there is a, I don't want to write this because there is a little bit of a difference between what we have been doing so far and over here, in the sense that the direction of arrows, the direction of morphisms will change. So I'll just keep it at this place. So again, there is a best construction over here. Now, to sum up, how can we put all of this, how can we make the whole effort of MacLean and Eilenberg to see all of this in a single formal setup that gave rise to the notion of a category? And if we see throughout these examples, there are a few features that we have used. Firstly, there is a strange symbol called an arrow, but an arrow comes up with two places, the source and the target. And the source and the target are always some kinds of objects. So that means the first part in the definition would be a set of sources and a set of, so these will be certain kind of objects. So this will be my set of objects. And there is a set of arrows, and the arrows come with two functions. Each arrow has a source and it has a target. So this is the, if this is the F, if this is the labeled as F, this is my source of F and this is my target of F. Then it is another thing that comes up is I have been using something called the composition over here, which was always the functional composition, but now I need to formalize it. So whenever I'm trying to formalize this, I have to look for properties. So how was I composing it? So I needed something like this. So I will say that a pair is composable provided the domain, so a pair like this is composable provided the domain of, or the source of F is same as the target of G. So that's the set of composable arrows. And what would be the composition then? Well, it will be a map, because that will give me a map. It's a kind of a multiplication. So I will say M of Fg, I will write this as F composed G. Obviously, I need to say what would be the source and the, so the domain of the composite is going to be this one, which is the domain of the second coordinate. So I can see from A2 there are already two other projection maps. So let me give this a separate color because it is automatically there in the structure, as I'm saying. The black ones are ones which are introducing. The others are in the structure itself. So let's say this is the first projection and this is the second projection. So source of the composite must be equal to the same as the source of the second projection. And the target of the composite must be equal to the target of the first projection, right? So P1 takes me to F and P2 takes me to G. Okay? So, good. It seems so far I have got hold of a structure, but there is yet another one, and that we have not used explicitly over here. For each object, there is a specific morphism which has the same source and the same. So if I take an object star, there is a morphism which has the same source and the same target, and it is called the identity morphism. And the identity morphism, so the source of identity is same as the target of the identity, and that is the identity map over here. Remember, these arrows over here are functions, okay, in this diagram that I'm drawing. So then I have this composition to be associative. So if I have a third one, then H composed F composed G is equal to H F G. This can also be written in terms of these equations again. And if I have F composed of the identity on star is F, and that is same as the identity on square times F. Okay? So a diagram like this, a configuration like this, along with these basic equations, is what was called a category. Obviously, every category comes in with its own structure. So these are its structure maps. And structure preserving morphisms are going to be its morphisms, and they are called functors. There is a third layer, and that was the most crucial observation that required, but that is still even, that is called the notion of a natural transformation. And truly speaking, each one of these transformations that we have seen so far, like associating, where is it? Associating the Grothendieck group of a monoid to a monoid, associating the free ring to a set X, associating the monoid ring Zm to a monoid M, or the tensor ring, each one of these, this process of associations give rise to functors. Furthermore, the comparisons that we were doing from X to ZX, from A to TA, each one of these are examples of natural transformations. But let's give another more something which we did not do, but something which might be how do I say, very quickly conveyable. Remember, in your linear algebra, when you take a finite dimensional vector space and you fix a basis, say its dimension is n, then you have a transformation going to Rn, which you call the coordinates of a vector with respect to this basis B. Well, this is an isomorphism, yes. So for each, what have you given me? For each such pair of a vector space and a basis, you have given me a linear transformation. I'm saying this is natural. In what sense? Suppose you give me another, this is exactly the sense of being natural. Suppose you have another vector space W and a basis, and you give me its coordinates. Whenever you have a morphism, a linear transformation from V to W, this morphism gets represented by a matrix with respect to this basis, right? And that is also a linear transformation. This matrix affects this as a multiplication by this matrix, right? So this process of associating each vector space to its Rn via this coordinatization. So the coordinatization is natural, irrespective of the vector space that you might take, irrespective of the basis you might take. When you transform the domain, when you transform V, you have a similar transformation on Rn. This is the syntactic side of the story. This is the geometric side of the story. So you have a similar transformation. So this is exactly the picture over here. When you change from your X over here, when you change, let me take a particular example, say, when you change your abelian group, where is that? When you change your abelian group A to another group B, yes. When you change your abelian group A to another group B, your tensor algebra changes in the same way. So this change doesn't get affected. Okay? So this kind of associations between two changes, functorial changes, is called a natural transformation. Natural in the sense that the transformation between these functors change naturally with the change of the arguments. So that's why it is called a natural transformation. With this I will stop, but I just want to say that I just want to add one more thing to this. Doing research in category theory, well, it is just like this. Initially, when people were doing research in certain symmetries, they were finding properties of certain symmetries and expressing them via certain equations and so on and so forth. With the advent of group theory, symmetries or groups of symmetries became certain examples of a general notion of a group. Based on the formulation that I have given, it seems that categories make a very natural expression for almost all topics which come to discuss sets with some structure and structure preserving maps. In that case, it is not just as for groups and symmetries. We do not work in a particular category. So a particular category of groups becomes an example for us. But we want to find out properties and investigate about further results about general categories which might elucidate either new theorems or explain very different theorems from very particular cases. So that is what is about a research in category theory. With that, I will stop.
Okay, thank you, Parthoda, for your nice and so much informative deliberation. And now I shall welcome questions from the participants if they have anything to ask. And also I'd like to request Arnab or Prashantoda that I saw that some of questions has already been posed in the chat box. So
Okay.
could you please convey these
Okay.
messages to Parthoda?
Okay. I am Prashanto Sena. One questions from Sujit Bhattacharya. Okay, Payal Kormakar, please give us an example justifying Ekman-Hilton principle.
The Ekman-Hilton principle actually says that suppose if you have a monoid M, so that means you have a set along with a binary operation and an identity. Okay? And suppose you have a second binary operation which commutes with this original binary operation that was given, then the Ekman-Hilton principle says that these two binary operations are same, the identities are same, and it is a commutative monoid. So it is not possible to have on a monoid a second monoid means already a set along with the binary associative binary operation with an identity. It is not possible to have on such a structure a second binary operation which commutes with it and is distinct from it. So that is the Ekman-Hilton principle.
Okay, thank you. Arnab? Okay. One question from Dr. Sheikh Sharif Hassan. Is the Sierpinski's topological space uncountable with zero measure?
Wait.
Yes, I am here.
Okay. Could you raise your question?
1 minute. The Sierpinski space has a set on the underlying set has exactly two elements. Let me call them 0 and 1. Now on a two-element set, how many topologies can be there? There can be the discrete one, there can be the indiscrete one. Well, the discrete one has too many open sets. The indiscrete one has too few. And the third possibility is to have one open set, which is not trivial. Okay? And that is exactly the Sierpinski space. So that's why the inverse images of that open set are precisely so if you take a topological space X and you take a map then the continuous map into the Sierpinski space, the inverse images of that open set are precisely your open sets of the topology. Right? So each open set defines you a map. Suppose let's take the element 1 being open. Then if you take an open set u from X and you take the function which takes everything in u to 1 and the rest to 0, that is a continuous function. Okay? And functions like this obviously determine your open sets. That's why open sets of a topological space are in one-to-one correspondence with functions from the topological space to the Sierpinski space. So we say often that the Sierpinski space represents the topology of a topological space. Did I make it clear?
Hello.
Actually,
Well, we have another question. Yes.
okay.
Another question from Antara Rath, that if the tensor ring is infinite, give an example. If the tensor ring is infinite, give an example. Actually, she want to know an example from tensor ring, infinite tensor ring.
Well, the tensor ring already contains Z.
Z, so it's always infinite.
Infinite.
Okay.
Yes.
Another question from Sadiqur Rahman. How do you relate this concept of category in the measure space?
Okay. Now, what is a measurable space? Well, you have a set and another kind of it's a set of subsets again closed under closed under countable unions and complementation, right? And your maps between measurable spaces are those whose inverse image preserve measurable space, subspaces. Well, that itself makes a category. So it's a specific example of a category. Just like topological spaces and continuous functions, which make an example of a category. So that's what I meant. Whenever you see a set with some kind of a structure and structure preserving maps, then obviously you are speaking about a category.
Okay.
So there.
Okay.
Yeah.
So, sir, we have more questions?
Yeah. Yes.
Okay. Kishore Chetri, he wanted to ask, does category theory predict algebraic structures other than vector spaces, rings, groups, etc.?
Yes. In fact, it does much more. It precisely, it is pretty well known now what is an algebra. And algebra, for that matter, one needn't even have not only have the classical examples, but for instance, frames, which I mentioned, they are algebras, but they have infinitary operations. But there's something more. Compact Hausdorff spaces. Compact Hausdorff spaces are also algebras over sets. And what is the operation? Well, the operation is an infinitary one. You tell me which points would you try to make close to which sets, right? So,
Okay.
Given any set, you first take the discrete space, which is a Tikhonov space, and then the Stonecheck compactification of that And that becomes the best compact Hausdorff space, kind of the free, just as we had the free ring. So it is the free compact Hausdorff space connected with the set X. And it has all the properties of free and free things, and whatever you do, generator business, think about generators, and all these things that you do in algebra works well for compact Hausdorff spaces, provided you rethink of these notions in a proper way, and for that you need a category theory.
Okay, one more questions from mathematics department PM. Name is not mentioned over here. Can you extend the same concept of bilinear map to the multilinear map?
Yes, the story is a little bit bigger, but let me try to make it short. Whenever we started with a binary operation in our undergraduate classes, unfortunately, present day algebra books, I don't find this anymore. We speak about associativity, and then there used to be a theorem called generalized associativity, where you used to, so associativity, the axiom exactly says that parenthesis for 3 symbols, if you don't change the order, doesn't matter. But generalized associativity actually says that parenthesis for any length, any finite length, doesn't matter. Now, the same question comes up over here also. As I said, the tensor becomes a kind of a multiplication of, as a kind of a binary operation on abelian groups. And I said that it becomes associative. And this associative actually satisfies this generalized associativity law, which is now called Maclane's pentagon condition. And with this, it becomes a correct representation, or what do I say? Correct substitute of a multiplication on a category, and that gives rise to this tensor product. And why tensor products now? The associativity therefore gives rise to 3 products, 4 products, 5 products, multilinear products, but with isomorphisms. It comes coupled with isomorphisms natural in each one of these coordinates. These isomorphisms were not present in the case of sets because there was only one set. There was nothing to transfer, things in sets. The world of sets is a little bit kind of static. Here, there is a dynamism there because the objects themselves are moving and the multiplication is defined on them. Associativity is defined on them. So you have to make sure that things are also moving along with. So yes, it comes with 3, 4, 5 multilinear things, but it comes in coupled with those isomorphisms, which are often called the coherence conditions.
Sure, yeah.
Okay, another question by Payal Karmakar. Does the category theory have any connection with the manifold theory? And also by Swarnajit Purohit, that give a real life example applied the concept of category theorems.
Please repeat the last question.
Please give a real life example applied the concept of category theorems.
Okay, so there is something called in fact, what I did today was more or less introducing the notion of universality, and a very quick step from here is something called the notion of an adjunction. And then after some manipulations, you will show that there's something called a right adjoint and the left adjoint, and the right adjoint preserves products and equalizers and so on. What happens is, I have shown that the underlying set functor from topological spaces to set has both a right adjoint and a left adjoint. So in particular, this functor has very nice properties. It preserves products, equalizers, as well as sums. And this gives just a 2-minute shortening of all that big chapter in general topology course known as weak topologies and strong topologies. But remember, the muscle is not removed. The muscle has been now transformed from a topology course to material in category theory, and that is now being applied to say that this is trivial. So it often happens that results in just quoting one of the greats, Peter Freud, in his book Abelian Categories, he writes, the sole purpose of category theory is to say what is trivially trivial. That means it just happens in so many cases that it seems then trivially trivial. This doesn't obviously mean to undermine several other endeavors. It is nothing new. People who were working just with symmetries, certain kinds of symmetries, often come and discover a new kind of a symmetry. But someone who came to know the notion of a group immediately knows what are the possible symmetries possible in a certain setup. So to him, the work of the previous kind was trivial. So similarly, here, since it is not only the case of a group, but the case of each and many others, there are many other categories which are not like sets and structures. So they are also examples of a general category theory research, or a study. So therefore, the more you abstract, things special become very trivial. But it doesn't want to mean that it is unimportant or really bad. That's not the case. So that's what I wanted to say.
So any more questions from the participants? If there are no questions from the participants, so I would like to thank Professor Parthabuddin Ghosh for delivering such a nice lecture, and I am handing over my session to Arnav Gupta to continue the next session.
Thank you, Vishwajit. So right now we have another speaker, Professor Mohammad Akbari Tutkaboni from Department of Pure Mathematics, Faculty of Mathematical Sciences, University of Gulian, Iran, and the session chair, Dr. Prashanto Sinha will act as a session chair in this session. So may I request Dr. Prashanto Sinha to conduct this session. Thank you.
Okay. Thank to Dr. Gupta for considering me as a chairperson of this session. I'm really honored to chair this session and to introduce Professor Mohammad Akbari Tutkaboni. Professor Mohammad Akbari Tutkaboni is presently Faculty of Mathematical Sciences in the Department of Pure Mathematics University of Gilan, Rast, Iran. His major field was harmonic analysis and semigroup compactification. He completed his PhD on compact left ideal in LUC compactification from a locally compact semi-topological group under the supervision of Dr. A.H. Riazi. His present field of research is Stonche compactification and ergodic-Ramsey theory. Today, he will deliver his lecture on LMC compactification of a semi-topological semigroup as a space of jet filters and some consequences. So I request Professor Tutkabori, please present your lecture. Thanks.
Thank you very much. Hi, everybody. I am very thankful for to the organizers of international webinar, especially Professor Sinha. Okay. Our talk is about LMC compactification of semi-topological semigroup as a space of Z filters and some consequences. First, I like talk about our aims in this talk, and we concentrate to subject in this talk. And the first, we describe semigroup compactification of a semi-topological semigroup as a space of filters, and then we obtain some algebraic relation on semigroup compactification by filter methods. Reference of this part are three work and three papers, and the last paper is extension of Talim Budak papers that she worked on discrete case. Finally, we state some combinatorial conclusions on amenable locally compact topological groups. We prove a big version of Furstenberg's correspondence principal theorem for amenable locally compact groups. And of course, we know that the Furstenberg's correspondence principal theorem is not true for locally compact groups. And final, we state Jeans theorem on amenable locally compact groups. So in this part, the first part, we define semigroup compactification. The first, we define semi-topological semigroup. Let S be a semigroup and S, which is also a Hausdorff topological space. We say that S semi-topological semigroup if left translation and right translation are continuous. If just right translation is continuous, we say that S is right topological semigroup. CBS here is denote CSR algebra of all bounded continuous complex functions on S with supremum norm, and let F be a C-star subalgebra of CBS. The spectrum of F here is denoted by S power F, and the spectrum is defined by the collection of all multiplicative means. In fact, SF is equal to set of all continuous functional on F, such that mu is mean and is multiplicative. That's this definition is multiplicative function. We say that F is an admissible C-star subalgebra of CBS if F F for every under left translation is invariant, and that's mean if for every f into in f and every x in s, we have this function belongs f. Also, for every multiplicative mean in s power f, and for every f into in f implies that T nu f belongs f. T nu f that's mean defined by this equation. We say that no, let F be an M-admissible subalgebra of CBAS. The set of all multiplicative means of F, which is denoted by S power F, equipped with the Gelfand topology, is a compact Hausdorff-Wright topological semigroup. The action, the binary action on SF is defined by this definition, and we know that above definition T nu f is defined by this, and this defined for every admissible subalgebra we can define we can obtain SF as a semigroup, and that is a right compact topological semigroup. And the evaluation mapping epsilon from S into a spectrum of F by this definition is a continuous homomorphism, and epsilon S is dense subset of S power F, and it is epsilon S is subset of topological center of S power F. We know we say that SF pair epsilon SF is semigroup compactification of S. Two important subset of S as an admissible subalgebra is called LUC and LMC. LUC is LUCS is a collection of all bounded continuous functions such that this function is norm continuous. LUC is a C-star subalgebra and is M-admissible. So the spectrum of this subalgebra is semigroup compactification of S. Also, we say that F is left multiplicative continuous if for every element of a spectrum of CBAS, that is Stonchak compactification of S, this function is a continuous and bounded function on S. The collection of all left multiplicative continuous function is denoted by LMC, and we can define LMC subalgebra of S by this definition. SLMC is the universal semigroup compactification. In fact, LMC is universal between all admissible subalgebra of CBAS. In a special case, when S is a locally compact topological group, we can obtain that LUCAG equal to LMCAG. So for locally compact group, LUC compactification is universal compactification, semigroup compactification of G. Now, we define semigroup compactification of as a space of Z filters for or for our work, we let F is we let F be a V and M admissible subalgebra of CBS, and for every F belongs F, we define zero set, and the collection of all zero set is denoted by ZF. And now we can define Z filter on this collection of of zero sets, and definition of Z filters is like you can see in book of Gilman's ring of continuous functions, and is well known. And also we can define Z ultra filter, and we know that by Zorn-Leva Z ultra filter exists, and we denote the collection of all Z ultra filter by Fs in this paper, and for every X belongs S, we define the principal Z ultra filter by X hat. In fact, X hat is the collection of all zero set that X belongs ZF. Now, we can obtain some relation between Z ultra filters and a spectrum of F. For example, if P is Z ultra filter, then there exists a multiplicative mean such that this intersection of element of Z ultra filter P equal to single set of mu. Also, for every element of a spectrum of F, we can find a Z ultra filter P such that again this relation is true. Of course, this correspondence is not one-to-one. We can obtain example that for example, if for a special subalgebra of CBAS, we can find some example that we don't have any one-to-one relation between Z ultra filters and multiplicative means. We can define a topology on FAS, the collection of all Z ultra filters, by this section of sets. We defined for every zero set A hat equal every Z ultra filters that A belongs P, and by this topology FAS is compact, but it is not Hausdorff. So we need to a space that this space became a Hausdorff space, Hausdorff and compact space. So we define a relation between Z ultra filters by this definition. We say that two Z ultra filters are equivalent if and only if this section, these two sections are equal. This relation is equivalence relation on Fs, so we can define a equivalence class for every Z ultra filter of on S, and we can define a quotient map, and for every Z ultra filter, we can define every Z ultra filter imagine on class P, and for every P for every Z ultra filter, we define P tilde by this section, by this intersection, and this help us for define A tilde as the collection of all P tilde such that A belong to A tilde for every Z filter of for every zero set, and we can define R equal to collection of all P tilde such that P this is this is a P. P is a Z ultra filter. The collection of R tilde complement when A is a zero set is a basis for topology on R, and R by this topology is Hausdorff and compact space, and the spectrum of F and R are homomorphic. No, we need define a binary operation on R. We know that SF is semigroup compactification, and no, we know that R is compact Hausdorff, and R and S and a spectrum of F are homomorphic, and we need give a algebraic structure to R. For every multiplicative mean in a spectrum of F, we define A mu, the collection of all Z zero sets such that ZF belong to this set. We can. It is obvious that this section is quotient class of P, and this definition is equal to P tilde. No, since that for every X in on S, we know that epsilon S is subset of S, subset of a spectrum of S, so we can define this definition, this binary operation on dense subset of a spectrum of F. A epsilon S S star A epsilon Y equal by this set. We can show that for this binary operation is a Z ultra filter, and this is equal to this Z ultra filter for every X and Y belong S. No, we since that epsilon S is dense in a spectrum of F for two net in S, when this net converges to mu and this net converges to nu, we define A mu S star A nu as this limit. By this definition, we can obtain that R and pair R and E is compact right topological semigroup, and E is an evaluation map is defined by this definition is continuous, and this function by this definition is an isomorphism. So the operation on S extends uniquely to R star. Thus, R is a semigroup compactification of S, and we can say that R and S and a spectrum of F are equal and isomorphic homomorphic topologically R and S power F are topologically isomorphism. So we can use element of a spectrum of F as Z filters. Now we can obtain some result on this area with use of filters. For example, we need to find pure Z filter. We say that G is as a subset of zero set is called pure Z filter. If for some Z ultra filter, if G is subset of P, implies that G is a subset of P tilde. For filter G, we define G bar equal to closure of G equal to all P tilde, such that for some Z ultra filter, G is a subset of P. And for two Z filters, we defined A O B by this definition, and we can say that if A and B are Z filters, then we can obtain that AOB is a filter. Every time A and B are filters, we can define A plus B equal to intersection of closure of A O B. So for two Z pure filters, and for mu and nu in a spectrum of F, we can obtain this relation between binary action between two filters. For example, A plus A mu is equal by this relation, and A nu plus A mu is equal to A mu nu, and this is equal to a previous action we defined on R, and also we can define A plus B. A plus B is a subset of this Z filters, and A mu plus A is subset of this section. As a consequence of this lemma, we can obtain that let A be a pure filter such that we have this relation, then A plus a closure of A is a subsim group of a spectrum of F. Now let B be a filter and A be is a zero set. We define this subset of S to this definition are different, but they help us for obtain some relation between algebraic structure of F compactification of S. For example, let be a filter, then the following statement are equivalent. Closure of B is left ideal of F compactification of S, and for every element of B, omega BA equal to S, and also for every zero set A in zero set as A, if interior of closure A contains closure B, then we have this set equal to S. Now let A be a pure filter, and then closure of A is right ideal of F compactification of S, if and only if this relation, if and only if A subset of A plus A mu for every element of, for every A mu in F compactification of S. Also, we have this theorem, let A be a pure filter such that A plus is a left ideal of F compactification of S. Then the following statements are equivalent. Closure of A is minimal left ideal of F compactification of S, and for zero set T, if this set is non-empty, then for every zero set P with this property, there exists a finite set such that this set belongs pure filter A. Also, let T be a zero set. If this set is non-empty, then for every zero set P with this property, there exists element in A and a finite set such that this set is subset of this subset of this set. Okay. And now the first part of our work is finished, and some concept maybe we consider by this method. For example, we can define by this method uniform point. We know that uniform point for indiscrete case, uniform point, the first we defined by cardinal of element of filter. With ultra filter, we define uniform filter, and we know that the collection of all the set of right cancelable element of Stonechek compactification contains a dense open subset of uniform point of S. And in topological case, PIM and Filali defined uniform point by another definition v dot use filter, and also Alastair, a student of Filali, defined uniform point on locally compact group with filter, but on topological semigroup we don't have yet uniform definition definition of uniform point. And of course I try to define a uniform point, but I like obtain this relation, this theorem, but I can't. And another concept of we can define by filter, for example, Rudin-Kessler order on this on topological group, and Rudin-Kessler order is a suitable concept, and we know that it is an important has an important role in Stonechek compactification, and Professor Heinemann consider Professor Heinemann and Professor Donashtaras consider to this definition as a independent chapter. Okay. No, I like go to some combinatorial method in a locally compact group, and by use Z ultra filter. And the first we like define density on locally compact on amenable locally compact topological groups. Let G be a locally compact group, and lambda be a left Harmager on G, and define and let PCG is the collection of all compact subset of G such that is not null, and we defined for net in PCG, and for a subset of G, lower density, upper density, and Banach density. And in this paper, just we consider to upper Banach density by this definition. Okay. Recall that group G is left amenable if and only if there exists a left invariant mean on a space of bounded real valued function on G under supremum norm, such that mu is positive linear functional, and normal mu is equal 1, and for every bounded function f and every x belongs in G, we have this relation. This means that mu is in left invariant, and positivity and this relation say that mu is mean. Okay. G is left amenable if and only if there exists a sequence of compact subset as Kn, of G with this property. This sequence converges to 0 for every x in G. Let F be a net in PCG, and then F is a left full net if and only if for every S in G, this net converges to 0, and as a consequence, we can conclude that for every compact subset of G, and this relation is true. Now we obtain a weak version of Freshenberg's correspondence principle theorem on locally compact group. You can see this. You can see this discrete version of this theorem in Heinemann and Estras's paper entitled density on arbitrary semigroup, and also and a weak version you can find this paper and this theorem in one of the reference of this type. Let lambda be a left Harmeger on amenable locally compact topological group, and let F be a Follner net in PCG, and let A be a subset of G such that the upper Banach density is positive. Then there is a countably additive regular measure mu on the set B of Borel subset of GLUC such that the first measure of closure of A is equal to Banach upper Banach density of A, and for every subset of G we have this relation. Also for every also mu is left invariant, and mu is a probability measure on GLUC. For proof of this paper, we let that A be a subset of J, and alpha is a upper Banach density of A, and let E equal to D product N, and we direct E by this method, by this definition, and for this direct we obtain a subnet of D such that this relation is true for this subnet, because for the first item we need this relation, and this help us we obtain this we proved the first result. Okay. Now let C denote the space of all bounded lambda measurable complex valued function defined on GLUC with uniform norm, and for every pair MK in E we define TMK from S into C by this definition, and since that GLUC G is a subset of GLUC, so this definition is well defined, and we observe that for every B subset of G, we have this relation, and also we obtain this, and finally we obtain this the last relation. Okay. Now, for every element of C, we define CF equal to as a subset of complex numbers, such that has this property, and the color, and let T from C into complex number be a limit point of this this collection of functions in the compact space of Y, and it is easy to establish each of the following statements are we can establish each of the following statements. He is continuous linear functional on C, and TKA closure of A equal to upper Banach density of A, and also this relation and this relation. By Riss representation theorem, T corresponds to a regular Borel measure mu on GLUC, and by the last conclusion, T is left invariant on C, and so mu is left invariant, and this complete our proof. As a combinatorial result, let lambda be a left Haar measure on amenable locally compact topological group, and let F be a Follner net in PCG. Let S be is in G, and A be subset of G with positive density. Then for every element of N, there exists a D in natural number such that upper Banach density of these sets is positive. Okay, now we concentrate on Green's theorem. The first, we define some definition. Let S be a semigroup, and let A be a subset of S. A is called Tick set if and only if for every finite subset of G there exists a element in X such that Fx subset of A. We say that A is synthetic if there exists a finite set H such that J is equal to this set. Also, we say that A is piecewise synthetic if and only if there exists a finite set such that this set is T. Gene theorem sorry for my mistake. I write gene, but it is gene. Gene theorem. Gene prove this theorem by non-standard analysis method, and he showed that for two subset of Z such that the upper Banach density their upper Banach density are positive, then A minus B is piecewise synthetic. After Jean Bergbook proved this theorem by ultrafilter method, and Jean theorem so has two different proof. We use Bergbook method for prove Jean's theorem for locally compact group, and we use Bergbook method in this talk. Let G be locally compact, non-compact topological group, and let A be subset of G. A is C synthetic if and only if for every compact subset of F there exists element X in G such that we have this relation. Like synthetic, we can define C synthetic, and C synthetic is A is C synthetic if and only if there exists a compact subset of H of G such that G equal to this set. But we know that H is compact, and maybe H is not finite set of G. So every synthetic set is C set, but maybe C set is not. Maybe C set. There exists C set is not a synthetic set. C synthetic is not synthetic set. Okay. Also, we can define the C piecewise synthetic if and only if for there exists a finite set such that this set is C synthetic. So we have this theorem. Let G be a non-compact locally compact topological group, and let A be a subset of G. A is C synthetic if and only if for every compact subset of G, null compact subset of G, there exists X in A such that Fx is a subset of A. Also, A is C piecewise synthetic if and only if there exists a synthetic set B and a C synthetic set C such that A equal to B intersect C, intersection of C. For example, for in a locally compact group, non-compact topological group, let F be a net in PCG. If A is a C synthetic subset of G, then upper Banach density of A is equal to 1. But also, if G equal to R, and then Q is C-synthetic subset of G, but upper Banach density of G is 0 for every net F in PCAG. Also, irrational number is not C-stick set, but upper Banach density of irrational number is 1, and for every net in PCAG. Okay, now we defined for a filter in GLUC and a zero set we define AP inverse equal to the collection of all element of X, element of G, such that XP belongs to closure of A. So we have this relation between element of GLUC and a subset of A, subset of G. AQ belongs to closure of A if and only if P belongs to this set, the closure of this set. Okay. Now let G be locally compact, non-compact topological group, and let F be a Wallner net in PCAG, and let A and B be two zero subset of G. Then there exists an E ultrafilter P on G, such that we have this relation between upper Banach density of this set and product of these two upper Banach density. Of course, I did not define E ultrafilter, and E ultrafilter is like Z filter, but we know that by Gilman's book, Rings of Continuous, entitled Rings of Continuous Functions, every maximal ideal in CBAG is correspondence with E ultrafilter, but this correspondence is not is one-to-one, and but there is not a one-to-one correspondence between maximal ideal and Z ultrafilter. So of course we can define GLUC as the collection of all of E ultrafilters, and so every element of GLUC could be defined as E ultrafilters or Z filters. Okay. Now, by this definition, we can obtain this theorem. Let G be locally compact, non-compact topological group, and let A be a measurable subset of G, and upper Banach density of A is positive. Then A inverse is C-synthetic, and so is synthetic set. And also we have for locally compact, non-compact topological group, if A and B are two zero subset of G and with positive upper Banach density, then A minus B is piecewise synthetic. And for proof of this theorem, since that upper Banach density of A and B are positive, so there exists an E ultrafilter P in GLUC such that C, by this definition, has positive upper Banach density, and and this implies that this set is synthetic, and since that X belongs to this set, so we have P belongs closure of X minus A B minus, and so for every finite set of this set, we have P belong this intersection. Therefore, for some element of G as T, we have this set. This finite set is subset of A B minus A B inverse. Because there exists an ultrafilter in beta in essential compactification as of G when G is defined as a discrete group, then P is subset of U, and since that A B inverse contains shift copy of all finite subset of the synthetic set, so this set is piecewise synthetic, and no, this type is this GM theorem is a common work with Professor Pantipatra, and then this is in fact our references, and Tallinn Papazian's paper by this entitled Filters and Semigroup Properties is important role in first part of our talk. Okay. Okay, my talk has been finished, and
Okay.
if you have
Any question for
I am
participants?
present. Okay.
You have already some problems, questions from the in the chat box, but I have one query to Professor Tutkagoni.
Yeah.
In the very beginning of your lecture, you told that for a locally compact topological groups, LUCG and LMCG are identical.
Okay.
So my question is that you have shown that you discuss LUCG in terms of the ultrafilters, right? So what is the use of further taking E filters to discuss the LMCG for the case of locally compact topological groups? Am I clear?
If filters alike Z ultrafilter obtain or in or work, and but if filters binary operation is very complicated, and for this I don't define define E ultrafilter in our work. But we can use Z filters instead E filters. Okay.
Yeah,
And,
that's it. Yeah,
and
that is my point. Once since you can handle LUCG by using the jet alpha filters, then what is the use of using the E alpha filters to discuss LMCG? Because in case of locally compact topological groups, these two concepts are identical.
LUC compactification and LMC compactification on locally compact group as a space of E ultra filters and as a space of Z filters are equal. Okay.
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 Okay. Sadikur Rahman asked, sir, hello. Sir.
Yeah.
Sadikur Rahman asked, does the left Haar measure can be defined in the sigma algebra Borel sets of any compact topological semigroup? If it can be defined, then is it unique?
Oh no, I have a request to you. Can you please keep your mic from your mouth away?
Okay. Yes. Is it audible now?
It is audible, but please keep your mic away from your mouth.
Okay.
Loudly audible.
Okay, now?
Okay, now you may continue.
Okay. So does the left Haar measure can be defined in the sigma algebra of Borel sets of any compact topological semigroup? If it can be defined, then is it unique?
No. For when work on when we work on sigma algebra, okay, that's related algebra is L infinity S and mu, okay, and so this space are not equal. For example, you defined real number. You consider to real number with natural topology and Borel set. With Borel set, you can define a spectrum, a compactification of real number that, and I state this space in previous talk in previous seminar, and this space this space is a semigroup compactification, but by natural topology we don't have any semigroup compactification on collection of all continuous bounded function on a real number. Okay.
Okay, one more question from, I am Prashantu Shena. One more question from Sadikur Rahman. Is there any application of Furstenberg correspondence in number theory? Can you hear me?
Furstenberg's correspondence in number theory is very important. For example, you know that Zemerdi theorem is proved by Furstenberg's correspondence theorem. Okay, and this theorem has important role in proof of Zemerdi theorem in number theory. But we know that Furstenberg's correspondence theorem is is a bridge between dynamical system and combinatorial number theory. Okay.
Okay, any other questions from the participants?
Okay. Is there any questions from participant? If it is not there, then I thank to the speaker, Professor Mohammad Akbari Tutkabuni, for his nice and lucid lecture. Okay, thanks.
Thank you very much.
Okay.
Okay.
Now I hand over to Dr. Ormo.
Okay, so we can move on to the valedictory session. So we have a vote of thanks, and the vote of thanks will be delivered by our respected HOD, Department of Mathematics, Professor Jagodbandhu College, Dr. Prashant Sinha.
Okay, before going to valedictory session, I first request all the participants from the both Google Meet and YouTube live stream, please fill up the feedback form. It is mandatory for receiving the e-certificate. Okay, thanks a lot. Okay, now it is the time of Thanksgiving. On behalf of the Department of Mathematics, I express my sincere thanks to our speakers, Professor Alan Dow, Department of Mathematics and Statistics, University of North Carolina at Charlotte, USA, Professor Partho Pratim Ghosh, Department of Mathematics and Statistics, University of South Africa, Dr. Vishwajit Mitra, Department of Mathematics, University of Burdwan, Professor Mohammad Akbari Tutkabuni, Faculty of Mathematical Sciences, Department of Pure Mathematics, University of Gilan, Rust, Iran, not only for their excellent and informative lectures, which inspires us and our students for our future endeavor, but they have given us their valuable time in trial meeting held 2 days back prior to the commencement of the webinar from their busy schedule. In fact, in this occasion, I express my special thanks to Vishwajit and Partho. I several times disturbed them, but they bear with me in every occasion with smiles face. I also express my heartfelt thanks to the chairs, Dr. Otoshi Debra, Department of Pure Mathematics, University of Calcutta, Dr. Vishwajit Mitra, and Professor Partho Pratim Ghosh for their continuous encouragement and advice and accepting our request to chair the session. I also express thanks to our principal, Dr. Subrata Kumar Ray, for his participation in this webinar. All the faculty members of the Department of Mathematics deserves a handful thanks for their relentless help and enthusiasm for conducting the same. Especially, I would like to mention the names of Dr. Sagar Moy Bagh and Mr. Humayun Kabir Laskar for their untiring effort to make this event fruitful. If I do not mention the names of our the effective role of the students of the Department of Mathematics, especially two postgraduate students, Mr. Kaulur Mojumdar and Shomujit Dey, we would commit a great mistake. In my introduction note, I have mentioned that the participants are from research institutes, namely ISER, ISI, universities and colleges, and from IIT and NIIT throughout the country and also from abroad. The students of my department, my colleagues, I express my sincere thanks to all the participants for making the webinar successful. Last but not the least, I express my sincere thanks to Dr. Kishore Mukhopadhyay, faculty member, Department of Physics, and convener of the seminar committee, for his technical assistance. I think at this moment he is in front of laptop and engaged in YouTube live streaming along with others in different places. Here, I would like to share with you few things. Initially, I thought the number of participants restricted to 250, but several requests came to me from outside and from the department. Then I changed my decision. And in fact, in the very first day, we observed that more than 350 participants have registered. In that occasion, we didn't have nothing to do with it. So our faculty members encouraged us, said, don't worry. But it was not so easy for us. 2 days prior to the commencement, we tried to YouTube live streaming, but we failed. At that time, a team led by the Professor Kishore Mukhopadhyay and consists of other members, Humayun Kobir Naskar, Shubhranil Chaudhary, and one of my PG students called Lal Mojumdar. And it is the result for their day-night labor. For that reason, we are successful to communicate this webinar to all sections of the participants. Once again, I thank to all. Okay.
Thank you, Prashantuda.
Okay. So I do expect some comments from our speakers, chairpersons, if you have, and any comments from any participants.
Very nice session.
Okay. Yes. Any comments from anyone?
Any comments, any queries, any suggestions from the participants?
After the webinar is over. Still, their Bishrit is there, Partho.
I just want to add one thing, add something like it's an excellent arrangement. You have made this seminar real success.
Okay, ma'am. Thanks.
Very nicely organized.
Okay. Actually, Partho is over here. Partho.
Yes, yes.
Okay.
Yes,
Actually, at that time, I missed out on questions from one participant. Actually, I would like to share that question. From Shubhajit Das, there is a precise definition of natural transformation between two functors. Can you kindly explain how does that apply to the particular example of linear algebra that you gave, the ones regarding finite dimensional spaces?
yes, I saw it and I have already replied on the chat box.
Okay,
Well,
thanks.
yeah.
Actually, one of my students, Sheikh Sorif Hassan, she raised a question, and I have raised the questions to you. You have answered it on the set measure 0 on Sierpinski space. Sharif, can you hear me? Sharif? Actually, Sharif requested me. I think he has some questions. Sharif, can you hear me? Okay, I think.
Yes. His question was whether it is uncountable.
Yes.
But it has only 2 points. So the question of uncountability.
Okay. no rays. Actually, he has seen in the factoral space. Actually, he told me later on over phone. Actually, I think he is not here. I told him to be here, and he's okay. Okay, so let us end our program.
I think Professor Dow is here.
Okay. Professor Dow is here. Okay, I'm requesting Professor Dow to say something.
You want me to say something? Well, I enjoyed the talks. I enjoyed the talks this morning. Thank you very much for including me. It's a it's a wonderful event. I think it's a great way to reach out to everybody. It's something you can't even do even without a pandemic. It's great.
Actually, it was possible only for you, sir. You, the speakers and chairpersons, we are really thankful to you.
Okay, Professor Dow, you are asking for yesterday. You are asking for a ring, which is PM ring, but not CX. I mean, not function ring. So in this context, I already sent you a mail. Have you seen that?
Yes, I have seen it. My question was more for your method of research, right? What are your sources of examples? Not did one exist? That's all.
Yes.
Yeah.
Actually, the purpose is different for me. Here I am not interested about too much examples. I am trying to extend those results to general PM rings, or maybe to an arbitrary rings if possible. So there are examples. Lots of examples are there. But yes, of course, examples are required to give counter examples, but that is why I could not give you the counter example about the whether Z is dense in Zi. So these things, and also there are many counter examples we need to clarify, but still we are searching for that, because PM rings are too specialized ring. It is very difficult to get PM rings so oftenly, because actually if you consider all those rings whose prime ideals are maximal, then those are also PM rings. But still searching for something which is different from all of these known examples, and that is why we need some example. But at present, I'm not interested our example, trying to generalize those concepts in general rings, how much we can do that. That's the purpose. Anyhow, the examples we should look for.
Did you ask me a question? I didn't.
No, I'm not asking you any question.
Okay, good.
Okay, Prashantoda, you may continue.
Okay. So we have reached our program is on the way of completions. If we are doing it at our own informally. Okay. To my colleagues from our department, do you have any queries to our respected speaker? Arnob, Humayun, Shagorma is there. Shagor?
Yes, sir, I am here, sir.
Okay. Do you have anything to ask our speakers?
No,
any questions?
I have an example of a PM ring, Biswajit Babu. CKX, if we consider a non-compact, locally compact space, then it does not contain identity. So it is not isomorphic to any CX or any Tychono space Y. But Parthoda have shown that it is a PM ring. Every prime ideal is contained in a unique maximal ideal. So
But it doesn't contain identity, right?
Yes, yes.
but I am very much passionate over identity.
Oh, okay, okay.
Then one example might be the ring of Berwan functions. It is a peer.
Okay, so
So,
maybe.
and I think that the way you prove that C star X is dense in CX, we can see that V1 star, that is a bounded Berwan functions, that ring will be dense in the ring of Berwan functions too.
Oh, I see.
And I guess that absolutely it's a guess. I haven't worked it out, but so far what I have seen from your lecture that CX is not dense in the ring of Berwan functions.
Oh,
It's not that, not dense.
okay. So
No, the Berwan functions are too big, too big. CX cannot be dense.
I see. Okay. Professor Dow, I just books on model theory. I shall look for it.
Okay. Oh, you
Sounds too much sounds coming.
Okay. Okay.
Someone has put the microphone.
Microphone
Yes.
off.
So I shall go into that problem what you asked here. Let's see how much I can proceed. So Prashantada, anything to say more? Hello.
Is Prashant here?
Can you hear me?
Yes.
Okay. One of my
you have any-
students, Sheikh Sarif Hassan, is there. Sarif, do you have any queries to our speaker? Arto?
No, I was trying to ask then that I learned Sierpinski set in fractals course. So I thought
Set or space? Is it set or space?
no, it's a set having some topological properties also. I mean, one can define topology over there as well. So I was thinking whether is there any kind of connection with that set.
No. The Sierpinski set is something else.
Something else.
Sierpinski.
It is an uncountable subset of ring vector space.
So are you talking about Sierpinski gas state, Sarif?
Yes. I was talking about that. I see.
That is something else. Sierpinski space is Sierpinski space
It's quite different.
is
It's finite.
2 point. It has only 2 elements.
I see.
It's a 2-point set and with 3 open sets.
I see.
So that's finite. I think he thought about the Sierpinski set or set.
Okay.
Okay.
And Prashantada, we may request Professor Tutkaboni to say something.
Okay. Yes.
No, sorry. Thanks for this seminar. Okay, I have to go, and if you let me, okay.
Okay. Partho.
Okay.
Partho.
Okay,
Yes.
you may leave, Professor Tutkaboni, since
Okay.
Thank you.
Thanks.
Thank you. Thanks. Sorry. Okay. Bye.
Bye.
Partho, will you say something about the webinar or the experience you have gathered from here?
Well, Professor Dow said it much better than I could have said. It is obviously a very, very nice endeavor, and this could not even have been done in normal times when we gather together and so on. So it was really a very nice thing, and it was very nice also taking part in it. I'll reiterate with Professor Dow.
Okay, yes, yes.
Okay.
Okay, okay. Okay. So let us complete over here. Let us say.
Yes, if there is nothing more to say, then let us continue.
Okay, okay, let us move. Okay.
So
Let us say goodbye.
Okay,
Yes.
goodbye.
Bye.
Thank you,
Thank
Professor
you.
Dow.
Thank you for being with us, Professor Dow. It's
Okay.
our great pleasure for being with
Exactly.
you the 2 days.
Actually, he has rescheduled it. Initially, he was not. It was not possible for him
Yes,
to
yes.
join the second day's webinar. Later on, he has rescheduled.
Yes.
Okay. Okay. Thanks a lot, Professor Dow.
All right then. Okay. Bye bye, everybody.
Okay.
Bye.
So
ঠিক আছে
আমরা
Okay.
তাহলে বেরোচ্ছি।
হ্যাঁ বেরোচ্ছে ওকে আচ্ছা
হ্যাঁ কিছু বলবি
না আমার কিছু তোরা একটু থাক না যদি পারিস আর আমাদের ডিপার্টমেন্টের ছেলে মেয়েরা যেন বেরিয়ে যাও না ছাত্র ছাত্রী এবং টিচাররা
কি কি বল আছি আমি বল
হ্যাঁ ঠিক আছে না গতকাল তো তুই চলে গেলি আর আমরা শুরু করতে পারলাম না আমাদের দেখি আমাদের ছেলে মেয়েরা কোথায় গেল
স্যার এগুলো সব রেকর্ডিং হচ্ছে স্যার
আচ্ছা ঠিক আছে
আমার মনে হয় এটাকে শেষ করে দেওয়া দরকার স্যার রেকর্ডিং তো কাজে লাগবে
না ঠিক আছে এটা আমরা একাডেমিক জিনিসটা করছি তো মানে আমাদের ইনফর্মাল ডিসকাশনের মধ্যে ম্যাথমেটিক্স ইজ देयर সো নো নিড টু বি ওরিড অ্যাবাউট ইট
হ্যাঁ কি বলছিস বল
বলছি কিছু না আমাদের আমি জিজ্ঞেস করছিলাম আমাদের ম্যাথমেটিক্স ডিপার্টমেন্টের টিচার বা স্টুডেন্ট তাদের যদি কিছু বলার থাকে দে ক্যান আস্ক ইন देयर ওন অ্যাট देयर ওন তোমরা তোমাদের মতো জিজ্ঞেস করতে পারো হুমায়ুন সুব্রনীল আর কে আছে কল্লোল সৌম্যজিৎ তোমরা এই সুযোগগুলো পাবে না তোমাদের যদি এনি সর্টস অফ কোয়ারিজ রিগার্ডিং ম্যাথমেটিক্স এনি সর্টস অফ প্রবলেম ইউ ক্যান রেজ ইউর পয়েন্ট ক্যান ইউ হিয়ার মি কল্লোল সৌম্যজিৎ অ্যাকচুয়ালি ইন্টারনেট প্রবলেম কল্লোল
হ্যাঁ হ্যালো স্যার
তোমাদের কিন্তু এই সুযোগগুলো পাবে না এইগুলো এই সেমিনারগুলো কিন্তু অর্গানাইজ করা তোমাদের জন্য
হ্যাঁ স্যার মানে এনজয় করেছি খুব এটা
if you have any sorts of queries any you can ask them সেই
না
জন্য
স্যার না
ওকে
হ্যালো স্যার
হ্যালো
ইয়েস ইয়েস
হ্যাঁ স্যার শুনতে পাচ্ছেন আমার কথা
হ্যাঁ হ্যাঁ
হ্যাঁ বলো 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 বলো
হ্যালো স্যার গুড ইভিনিং এখন নাইট স্যার অ্যাকচুয়ালি এই যে কোশ্চেনটা আমি করে যে কোশ্চেনটা ছিল না স্যার মাল্টিলিনিয়ার লিনিয়ার ম্যাথমেটিক্সটা এটা যদি একটু আরেকবার বলতে পারতেন ভালো হতো এটা আমার কোশ্চেন ছিল বাট আমি ক্লিয়ার করতে পারিনি
সেটা পরে করে দেবো এইটাই তো না অন্য কোনো প্রশ্ন আছে
না না আর কিছু না
তুমি যেটা বলতে চাইছো
হ্যাঁ স্যার
কে 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 জানো নামটা ভুলে গেলাম
সৌম্যজিৎ দে
হ্যাঁ 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 যেটা তুমি বলতে চাইছো সেটা হচ্ছে আমি এই ম্যাপটার কথা বলছিলাম আমার একটা বেসিস আছে কোঅর্ডিনেটস
পার্থ তুমি কি শেয়ার করবে স্ক্রিন বোঝানোর জন্য
হ্যাঁ শেয়ার
করেছি এখন কি করবে আপনি
না
হ্যাঁ করছি তো
আমি দেখতে পাচ্ছি
এবার দেখছো
না না হ্যাঁ এবার রাইট নাও ইট ইজ প্রেজেন্ট
এবার আসছে স্যার
এবার আসছে
এইটা বলতে আমি যেটা বলছি যে যদি আমার একটা বেসিস থাকে বি আমি যদি ধরে নিই ডাইমেনশন অফ ভি ইজ এন আর বেসিস যদি আমি বলি v1 v2 vn, এটা বলার কোঅর্ডিনেটসটা কি করে, এইটা যদি আমায় এটাতে নিয়ে যাওয়ার মানে হচ্ছে, এই কথাটা বলার মানে হচ্ছে ভি এর ইউনিক রিপ্রেজেন্টেশন ইন টার্মস অফ হচ্ছে এইটা, এটা ইউনিক। বেশ, তাহলে আমি ভেক্টর স্পেসটা এদিকে, তার মানে আমার দুটো ফাংটার লাগবে। একদিকের ফাংটারটা বুঝতে পারছি আইডেন্টিটি ফাংটার, অন্য দিকেরটা এইরকম একটা। তার ক্যাটেগরিটা কি হবে? ক্যাটেগরিটা হবে যার অবজেক্টস গুলো হচ্ছে পেয়ার্স। ভি হচ্ছে ভেক্টর স্পেসটা, ফাইনাইট ডাইমেনশনাল, আর এটা হচ্ছে বেসিসটা। আমি আর নিচ্ছি, এখানে আর এর কোনো বিশেষত্ব নেই, ইট ক্যান রিপ্লেস ইট বাই এনি ফিল্ড। ওকে, নাও আর মরফিজমস গুলো কি? দে আর প্রিসাইজলি লিনিয়ার ম্যাপস, আর কিছু, আর কেউ না। মরফিজমস গুলো হচ্ছে জাস্ট লিনিয়ার ম্যাপস। আচ্ছা, এই দিকের ফাংটারটা কি? আমি এ থেকে আমি এরকম ভাবে লিখতে ভালোবাসি, এই ফিল ইন দ্য ব্ল্যাঙ্কের মতো। ভি উইল গো টু আর টু দি পাওয়ার ডাইমেনশন অফ ভি, সরি নট ভি, এখানে হবে হচ্ছে ওই পেয়ারটা W and A would go to dimension of W, আর এখানে যখন একটা মরফিজম আছে তখন আমার জানা আছে যে এই মরফিজমটার দরুন আমার এখানে একটা মরফিজম আছে। হোয়াট ইজ এফ স্টার? এখান থেকে যদি আমি একটা এক্স নিই, সেটা এই মরফিজমটা কি করছে না, এই এফটার যে ম্যাট্রিক্সটা ফ্রম বি টু এ, সেই ম্যাট্রিক্সটা দিয়ে মাল্টিপ্লাই করছে। ওকে, so that is this map F star. So now obviously এটা কম্পোজ করলে G composed F এর স্টার অবশ্যই হচ্ছে G star composed F star, matrix multiplication, আর কিছুই না। আর identity of V, which is nothing else but identity matrix linear transformation, সেটা কি হবে? সেটা হবে the identity map, identity of, so this is a functor. তাহলে এইবার ন্যাচুরাল ট্রান্সফরমেশনটাকে একদিকে হচ্ছে আমার আইডেন্টিটি, আর আরেক দিকে হচ্ছে আমার আর টু দি পাওয়ার ডাইমেনশন, এই ফাংশনটা। ন্যাচুরাল ট্রান্সফরমেশনটা হচ্ছে কোঅর্ডিনেটাইজেশন। ইনফ্যাক্ট এটা শুধু ট্রান্সফরমেশন না, এটা হচ্ছে একটা আইসোমরফিজম। প্রত্যেক কটাই হচ্ছে আমার আইসোমরফিক, মানে বাইজেকশন। বাইজেকশন শুধু না, লিনিয়ার আইসোমরফিজম। So this is the natural transformation. Is it clear?
হ্যাঁ স্যার। স্যার আমি অ্যাকচুয়ালি ক্যাটাগরি থিওরিটা অত ভালো আমি মানে কোনোদিনই পড়িনি অ্যাকচুয়ালি স্যার। আমার মনে হয় আমি যদি স্যার এদিকে আপনি যেটা ভেক্টর স্পেস নিয়েছেন সেটাকে যদি আমি এম এন ক্রস এন আর নিয়ে, আর রাইট সাইডে যদি আমি আর টু দ্য পাওয়ার এন নিয়ে আমি সেম ভাবে তো ডিফাইন করতে পারবো একটা ম্যাপ।
বুঝলাম না, রাইট সাইডে তুমি কি নেবে?
আমি বলছি লেফট সাইডে আমি যেটা আপনি ভেক্টর স্পেসটা নিয়ে নিয়েছেন, সেক্ষেত্রে যদি আমি
হ্যাঁ।
ম্যাট্রিক্সেরটা নিই, ম্যাট্রিক্স এম এন ক্রস এন একটা, আর রাইট সাইডে যদি আমি r টু দ্য পাওয়ার n স্কয়ার নিই, তাহলে তো আমি স্যার সেম ভাবে আমি একটা ক্যাটাগরি ওখানে পাবো।
ক্যাটেগরিটা পেতে গেলে কিছু বিশেষ অবজেক্ট দিলে হবে না, তোমাকে সমস্ত ধরনের অবজেক্ট ওই টাইপের নিতে হবে।
অ্যাকচুয়ালি ক্যাটেগরি ইজ দ্য ইউনিফিকেশন কনসেপ্ট, ইউনিফাইড।
সমস্ত ওই ধরনের অবজেক্ট নিতে হবে। সেই জন্যই আমি বলেছি যে অবজেক্টস গুলো হচ্ছে ফাইনাইট ডাইমেনশনাল ভেক্টর স্পেসেস, এবং এটা একটা এটা
আচ্ছা আচ্ছা। আরেকটা স্যার আপনার কাছে আরেকটা রিকোয়েস্ট আছে স্যার, আপনি কি আগের স্লাইড গুলোকে ডিলিট করে দিয়েছেন? সেটা কি পাওয়া যাবে আমাদের?
সেটা কি পিডিএফ হিসেবে চাও?
পার্থ,
হ্যাঁ স্যার, কিছু একটা
লেকচারটার একটা রাইট আপ দিয়ে দিবি না, দিস না, তাহলে আমরা প্রসিডিং
স্লাইড গুলোই আছে তো।
না, স্লাইড থাক, তবে একটা রাইট আপ দিয়ে দিবি।
রাইট আপ?
হ্যাঁ, পুরো আমরা একটা প্রসিডিংস বার করতে চলেছি আর কি। বিশ্বজিৎ বলেছে, আমার ভুলে গেলাম আর কি, অ্যালান ডাও আর
অ্যালান ডাওকে আমি গতকাল লিখেছিলাম, বাট হি ডিড নট রেসপন্স। কিন্তু উনি মেল দেখেছেন বললেন, ফলে আমি জানি না উনি দেবেন কিনা।
ও আচ্ছা,
রাইট আপ লিখতে গেলে প্রচুর লিখতে হবে।
একটু লিখে দে, ক্যাটেগরিটা লুসিলি বললে যাতে একটু একটা ফর্মাল ডেফিনিশনে পৌঁছে ছেড়ে দিলেই হবে আর কি। মানে ফর্মাল ডেফিনিশনে তো এখনো পৌঁছালাম না আমরা।
পৌঁছেছি তো, লাস্টে পৌঁছালাম।
হ্যাঁ, লাস্টে
পৌঁছালাম, সেটাই ফর্মাল ডেফিনিশন।
ওইটাই যদি একটা দেয়া যেত আর কি।
মানে প্রচুর লিখতে হবে, মানে এই খুব ছোট জিনিস হবে না।
এটা লিখে দে একটু কষ্ট করে।
মানে এখন এই মুহূর্তে করা খুব ডিফিকাল্ট।
মাসখানেক বাদে বা
তার চাইতে লেকচার দেওয়া অনেক সোজা।
সে তো ঠিকই না, একটা আমরা এটা বার করবো আর কি, সেই জন্যই আমার রিকোয়েস্ট। আমি দেখি প্রফেসর ডাউকে আমি একটা রিকোয়েস্ট করব, যদি উনি পাঠান। টুটকাবনিকে একটা পেপারে বোধহয় ওটা ওনার পক্ষে একটু অসুবিধা হবে দেয়ার, যদি অন্য ভাবে দেন তা আলাদা কথা। যেহেতু এটা পাবলিশ পেপার বা ইট ইজ গোয়িং টু বি পাবলিশ, সেক্ষেত্রে ওর বোধহয় অসুবিধা হবে ওই নামে। যাই হোক, এবার তবু রিকোয়েস্ট করে দেখবো।
মানে পুরো মালটা লেখা খুব চারটিখানি কথা হবে না, মানে অনেকখানি লেখা হবে। এবং
অ্যাকচুয়ালি আমরা যে ধরনের বই ফলো করি আর কি, ক্যাটেগরি থিওরিতে জাস্ট বিগিনস উইথ দ্য ডেফিনিশন। কিন্তু এই যে একটা ফর্মাল ওয়ে, কালকে একদিন আমাদের ট্রায়াল মিটিংয়ে বেশ সুন্দর বলছিল, আজকে তুইও যেটা বললি অ্যারো ট্যারো দিয়ে, এই যে মোটিভেশন অফ দ্য সাবজেক্ট, এটা কিন্তু খুব দারুণ। এই জন্য আমি চাইছিলাম যে একটা মোটিভেশন পাওয়া যায়, হাউ টু রিচ আওয়ার ক্যাটেগরি থিওরি বা ইউনিফাইড ফর্ম অফ আওয়ার, সেই জায়গাটা পেলে খুব ভালো হয়।
এখন বিশ্বজিৎ, মানে যেটা সবসময় আমি করতে রাজি আছি সেটা হচ্ছে যে কেউ যদি শুনতে চায় তাহলে প্রথম থেকে আমি বলতে রাজি আছি, তাহলে সেরকম সেমিনার করলেই হয়।
আচ্ছা আচ্ছা আচ্ছা, ঠিক আছে।
তা সেরকম সেমিনার যদি অ্যারেঞ্জ করতে পারিস তাহলে আমি বলতে রাজি আছি।
হ্যাঁ, ক্যাটেগরি থিওরি তাহলে আমাকে সিরিজ অফ সেমিনার অর্গানাইজ করতে হবে, বেশ একটা ভালো জায়গা, সাইজেবল জায়গা পৌঁছতে গেলে।
সাইজেবল জায়গা মানে কি? এখানে তো আর তোর ঘরদোর লাগছে না।
না না না, ঘরদোর নয় আর কি, মানে বেশ কয়েকটা লেকচার আর কি। মানে সাইজেবল লেকচার মিন্স আই ডু মিন দ্য নাম্বার অফ সেমিনার্স মাস্ট বি গুড।
সেমিনার যদি
এরকম,
আচ্ছা বিশ্বজিৎ বলতে চাইছিস?
সেমিনার যদি করো পার্টিকুলার টোপোলজিতে, এই পার্টিকুলার একটা সাবজেক্টে করো, ওই জেনারেল সেমিনার করে কোনো লাভ নেই।
না না না, মোটামুটি দেখো,
ক্যাটেগরি থিওরি করতে চাও তাহলে ক্যাটেগরি থিওরিতেই করো, সেক্ষেত্রে জার্নালিস্টকে পাবে।
জার্নালিস্টকে পাবি, রাইট?
না সেটা ঠিক আছে না, আমাদের এটার উদ্দেশ্য ছিল যে আমরা 2018 পিজি ডিপার্টমেন্ট খুলেছি, সেই জন্য আমরা টোপোলজি অ্যালজেব্রাটা চেয়েছিলাম। আমরা যদি হ্যাঁ, অফকোর্স আমি তো সাজেশনটা নিচ্ছি বিশ্বজিৎ, যদি করতে চাই একটা কোনো একটা সাবজেক্টে আমরা কনসেন্ট্রেট করবো লেটার অন। এখন এটা আমাদের উদ্দেশ্য ছিল অ্যালজেব্রা এন্ড টোপোলজিকে যদি একটা জায়গা, পার্থ অ্যালজেব্রার দিকটা বা তুইও অ্যালজেব্রার দিকটা অনেকটাই ধরেছিস, সেই জায়গা কিছুটা আমার মনে হয় ফ্রুটফুল হয়েছে আর কি। আমাদের স্টুডেন্টরাও কিন্তু এটা আই থিঙ্ক দে হ্যাভ রিচড টু ইয়োর লেকচার।
দেখ, এখন ইট হ্যাজ কাম টু সাচ এ স্টেজ যে অ্যালজেব্রা আর টোপোলজি
না, দেয়ার ইজ নো,
এবং এই ভাগগুলো
ওরা খুব ডিফিকাল্ট।
না না, শুধু ডিফিকাল্ট না, দে আর ননসেন্সিক্যাল নাও। They don't make any sense.
Exactly.
So it is not about
actually what said Tutkaboni, topological group, topological semi group, their algebraic properties there.
তো এখন সেই কারণে আমি বলছি যে it is much more about structures and structure preserving maps.
Exactly.
So সেই পয়েন্ট অফ ভিউ থেকে যখন দেখা হচ্ছে তখন অনেক কিছু বেরিয়ে আসে এবং which are much more fundamental. তো সেইখানে algebra, topology, compact Hausdorff spaces, they are also algebras.
Exactly.
Equally well as algebras like groups.
Exactly.
তো সেখানে তুই কি করে ভাগাভাগি করবি, আর তুই যেমন ভাবেই ডেফিনিশন নে না কেন, তোর কমপ্লিট ল্যাটিসেস আর নেভার অ্যালজেব্রাস। তো ভাগাভাগিটা কি করে করবি?
ভাগাভাগি
এখন সেটা সেই পয়েন্ট অফ ভিউটা দেওয়াটা এক, আর অ্যালজেব্রা টোপোলজি মানে যেটা বিশ্বজিৎ বললো, কোনো একটা টপিক ধরে সেইটা নিয়ে উইকলি সেমিনার করলেই হয়। উইকলি সেমিনার হবে, কি আসবে, কি আসবে না আসবে।
Actually, it is the new venture from our part. Okay, later on we'll do it. এর পরের দিকে আমরা এটা চেষ্টা করবো আরো, যাতে আমি সাজেশন গুলো নিচ্ছি, নিয়ে দেখা যাক পরে যদি আমাদের ছাত্রছাত্রীরা যদি এই ব্যাপারে ইন্টারেস্টেড হয় তাহলে আমরা অর্গানাইজ করার চেষ্টা করব।
হ্যাঁ, উইকলি চলছে। এখানে যেরকম সবসময় একটা উইকলি সেমিনার চলে।
হ্যাঁ হ্যাঁ, না আমি তোদের লেকচার গুলো কিন্তু অনেকটাই, যদিও আমরা কেউ কাউকে দেখতে পাচ্ছি না, বিশ্বজিৎ বা তোর বা এরন্ডা, এই সেমিনার গুলো অনেকটাই কিন্তু বেশ আমরা কানেক্ট করতে পারছি। এভাবে লিখে লিখে করা, ইটস এ নাইস অ্যাপ্রোচ।
প্রশান্ত, এবার উঠি।
হ্যাঁ হ্যাঁ হ্যাঁ, ঠিক আছে, ওকে, থ্যাঙ্কস এ লট পার্থ, বিশ্বজিৎ। ওকে
ওকে
ওকে ওকে, অনেক আমাদের জন্য অনেক ডিস্টার্ব করছি দুজনকে, পার্থ এবং বিশ্বজিৎ।
না, একাডেমিক কাজে তো ডিস্টারবেন্সের কোনো ব্যাপার নেই। নন একাডেমিক হলে অবশ্যই ডিস্টার্ব ফিল করতাম।
না না, পার্থকে ঘুম থেকে তুলে দিয়েছি।
আজকে সবচেয়ে বড় কথা, আজকের ঘুমটা বাতিল করে দিলি দুপুরে।
এত ঘুমোতে হবে না।
না না, পার্থ আমাকে বলেছে, ওর সঙ্গে তো আমার কন্টিনিউয়াস হোয়াটসঅ্যাপে কথা হচ্ছে এবং ফোনে কথা হচ্ছে, কেন আমাদের টাইম জোনটা তো একটু ডিফারেন্ট, ওই জন্য একটা প্রবলেম হচ্ছিল। ওর মাঝে মাঝে ওর ঘুমের সময় আমি ওকে বিরক্ত করছি।
বেশ করছিলে। ঠিক আছে,
ওকে ওকে বিশ্বজিৎ, পার্থ, ওকে
ওকে
ওকে, থ্যাংক ইউ।
স্যার রেকর্ডিংটা একটু বন্ধ করে দিন, ওটা চলছে।
হ্যাঁ, এবার করে দিচ্ছি। শোনো, এতক্ষণ আমাদের ম্যাথ সিরিজ আলোচনা হচ্ছিল। ওকে, বলো।
আচ্ছা, রেকর্ডিংটা স্যার ওটা বন্ধ করে দিন।
হ্যাঁ দাদা, রেকর্ডিংটা আবার